So for the next module, we'll need something known as cross entropy. So we'll just try to make some, develop some intuitions for cross entropy and get to the formula for that. And then I'll tell you how it relates to the problems that we deal with. Okay. So first, let's start with something simple, that what is it that we're trying to do. Okay. So with that, I'll give you an example and I'll ask you a few questions, and then from there we'll slightly try to go towards cross entropy. So now suppose you have an urn which has thousands of balls, and these balls are of 3 different colors, which are red, black and white, say, right? So you have an urn which has 3 different types of, and there are many such balls which you have put in it. And since you have put in it, you know how many red balls are there, how many blue balls are there, and how many white balls are there. So for you, it's very easy to compute the probability of each of these things, right? So that's, say your probability is 0.25, 0.35, and 0.4. Okay. Now talking more formally, what is happening here is that you have a random variable x which can take on the values red, blue or white, right? And this is the probability of each of those, or the random variable x taking any of these values. Okay. So this is the setup. Now I am your friend and you tell me that you can peep into this urn. You cannot actually take out all the balls and count them and estimate the probability, but you can just take a look into this and try to give me an estimate of what are these probability values. That means what is the value, so what is the probability that x is equal to red, or x equal to white, or x equal to blue. So I just take a look at it, turn it around a bit and try to get some feel, okay, I see a lot of red balls but a fewer blue balls or white balls and so on. And based on that, I make my guesstimate, right? So I just say that maybe these probabilities are 0.35, 0.45 and 0.2, right? So this is actually the true distribution. I'll call it as P, right? Because this is the correct one. And what I have estimated, I'll call it as Q. Okay. And remember now, P has, you can think of P as a vector which has these 3 values, P1, P2, P3, because there are 3 possible events here. And similarly, Q has 3 values, Q1, Q2 and Q3. So in this case, I clearly know that I'm wrong, or when I give you these values, you know that you're wrong. So you tell me that whatever you have estimated is wrong. Then I obviously ask you, okay, tell me how wrong was I? So how would you give me that number? Right? That's the thing that we are interested in. So the general problem that we are interested in is that there's a true probability distribution and there is an estimated probability distribution, and we want to find out how bad was the estimation. Okay. Now, can you tell me a simple way of computing this? It may not be correct, but still it makes sense. You could just take the squared error. So what you're essentially telling me is that you could just treat these 2 as any other vector, right? And you could take the squared error difference between these quantities. So what you're telling me is this, where I goes from 1 to 3. Okay. So this is one valid way of doing this. But then we are ignoring the fact that this is a distribution and hence it has certain properties, that the sum of the elements is 1 and so on, all of them are positive and things like that. So we are ignoring those kind of things. We are completely ignoring the fact that we are not dealing with a normal vector, but a spatial vector which happens to be a distribution. Okay. So now we want to find out a more principled way of computing the difference between 2 distributions. And in practice, why are we interested in this? Because we'll always have a true distribution and a predicted distribution, right? So that's what we want to do. We have some way of computing it, but we want a better way of computing it. Okay. Now, let me make a case for why do we care about such differences, right? So let me take a simple case of a classification problem. Okay. And to motivate that, I'll start from a different example and then I'll come to the classification problem. Suppose there is a tournament going on and there were 4 teams which reached the semi-finals. Let's call them A, B, C, D. Okay. Now you were following the tournament up to the semi-finals, and after that you didn't watch the tournament and you don't know who eventually won. But the tournament is over and someone has won it. Okay. I actually watched the tournament and I know that B has won it. Okay. Now can I express this in terms of a probability distribution, right? So first let's look at what is the random variable here. What is the random variable here? The team which won, right? So that's my random variable and it can take one of these 4 values. Okay. Now I know that team B won because I saw the tournament and I have seen that they won. So now how can I write this as a distribution? What does the distribution comprise of? It comprises of these probabilities assigned to each of these events. And there are 4 such events here. So how do I write this distribution? So what you're telling me is I could write it as 0, 1, 0, 0. So essentially you're telling me that all the probability mass is focused on one of these outcomes because that's the certain outcome. That's already happened. No one can change it. So that's the outcome for this tournament. So I know that the probability of that event is 1 and everything else is 0. So in other words, the probability that the random variable x takes on the value b is 1 and everything else is 0. Right? So what I'm trying to tell you is that even for a certain event, you could still write it in terms of a distribution where all the mass is focused on that event. Okay. Now again, I'll bring the same setup that I did not watch the tournament after the semifinals. So now you ask me, give me your prediction, which team would win? Okay, or this is the prediction which I made just after the semifinals, or sorry, just before the semifinals, that I think one of these teams is going to win the tournament and the chance of each of them winning is something like this. So I know the teams, I follow this sport and I probably know that okay, B has a very strong team and they have a very good record in the past few months and so on. So maybe they have a higher probability of winning. So these are the numbers which I assign. Okay, fine. Now again I have made an estimate. Was my estimate perfect? When would it have been perfect? If I had predicted with certainty 1 that B is going to win. But I was not willing to bet everything on B. So I said there's a very high chance it will win, but there's still a chance that there could be some surprises. Okay. Now how wrong was I? Now again can you tell me what is P and what is Q here? This is the true distribution and this is my predicted distribution. And what am I interested in again? The difference between them. How wrong did I go? And what is a simple way of doing this again? Squared error loss. So again, this is what my formula would look like. Okay. So this is fine in this toy case, but why do we care about in real life examples that we are going to deal with in machine learning, right? So in machine learning, we'll deal with a lot of problems which are classification problems, okay? And in classification problems, you would again have this setup where you have a label. You could think of the label as a random variable and it could take off one of many values, right? So I'll again assume that it could take, suppose you're trying to take a picture of fruits, okay? And you're trying to classify them, okay? And I could again think that I have 4 fruits, say apple, banana, cherry and dragon fruit, okay? And this random variable can take one of these 4 values depending on the image that I'm seeing, okay? Now I've been given some training data. So for every training data, I've been given an image and I've been given the correct label. So for that training data, what is this distribution? Suppose I've been given the image of a banana. What does this distribution look like? 0, 1, 0, 0. Right? Again, I have seen it, so I know it's certainly a banana. So I don't have any confusion. All the probability mass is focused on that. Now the same image we are going to show to one of our models, okay, and it is going to make a prediction, and we'll again ask it to give us a distribution. The model will give us values perhaps like this, okay. So this is the model's prediction. Again, the model has given us a distribution and we have a true distribution, and we are interested in knowing how wrong the model was, so that we can correct the parameters of the model. So this is our dash function, loss function, right? So our loss function is some notion of difference between P and Q, right? And so far we have been dealing with a very simplistic notion of this difference, which is just the squared error loss, okay? And we want to do something better than this, right? So what I have told you is that you could always have a true distribution, always have a predicted distribution, and you would be interested in finding the difference between them. That's the first part. The second part is that even when you are given something with certainty, you could still write it as a distribution such that all the mass is focused on that event which has happened. right? Which was the label was banana in this case, okay? And then you could still predict this from your model. And now you're interested in knowing how wrong your model went, because that's the loss function that you'll use. And then you'll try to update your parameters with respect to this loss function. Right? So that's the setup that we are interested in, okay? Okay, so that's, so I made a case for why we need to find differences between two distributions. How to do it in a more principled manner, we have not seen that yet. We'll get to that, okay? So before I get that, I also need to tell you something about expectations, okay? So let's return to our sports example where there were 4 teams, okay? And say based on pundits in that sport, they have said that these are the probabilities of winning, okay? And now you are into betting, and you place your bets on these teams, and you place your bets in a way that suppose team A wins, then you'll end up winning 10k rupees. If team B wins, then probably you'll end up winning 5k rupees. And if team C wins, probably 10k. And if one of the other team wins, maybe you'll end up losing money or something like that, right? Now, you want to know what is your expected reward, okay? So now let's see what is happening here. This was a random variable which could take on one of these 4 values. These are the probabilities of the random variable taking that value, taking on the value A or taking on the value B, C and D, okay? This is your value or the gain or the profit associated with the random variable taking one of these values, right? So you have a random variable, you have a probability associated with every value of the random variable, and you have some gain or value associated with every value of the random variable. Now, how do you calculate the expected gain or expected profit, which is this? There's a 30% chance that you will earn 10k. There's a 40% chance that you will earn 5k. There's a 20% chance that you will earn 10k and 10% chance that you will lose 30k, right? So the way you will compute it is that, and this is the simple expectation formula, which is the probability of, now the event here belongs to A, B, C, D, right? This is one of the 4 teams that will win. Probability of that event happening into the value associated with that event happening, okay? Is it a fair computation? You get the intuition that this is how you will compute the net reward that you have, okay? So this is how you compute the expected value with respect to a particular distribution, okay? So this is the background that we need. Now I'll just go on to the next slide. And now we'll talk about entropy first, perhaps information content first, then entropy, and then cross entropy, okay? So now what is information content? So now again, let's take the same case that we have a random variable which can take on values A, B, C, D, okay? Now what we're trying to say is that if I know a certain thing, what is the information that I have gained? So you and I are talking, you tell me something, okay, and I want to see whether my information was enhanced, whether my knowledge was enhanced. That's how we'll quantify information content, okay? So if you're talking to me and you tell me that my name is Mitesh, there's 0 information content for me, right? Because I already know that. There's no surprise in that, okay? But if you talk to me and you tell me that today there's going to be a lunar eclipse, then there's a possibility there's some information content gain for me, right? Because that's not an event which happens every day. If you just tell me you'll see the moon today and you live in a region where it's not typically cloudy, then there is no information gain there, right? So what do you see here? When is the information gain high? When the event which happens is a very surprising event. And how do you say surprise in terms of probability? It's a very low probability event, right? So if there's again this tournament and say D was the weakest team in the tournament and A was the strongest team in the tournament. If you come and tell me that D won, then I would be really surprised. That's some information which I had gained. But if you tell me that A won, then probably I already knew it at the back of my mind, right? Because A is clearly the strongest team in the tournament and there's no information gain for me. So one thing that we are trying to establish that the information content the information content of an event is inversely proportional to the probability of the event. That's a fair intuition, okay? Fine. Now I want I'm still talking in terms of vague things. I'm saying it's inversely proportional, but I still need an exact function so that I can compute it. So I want a function where I plug in the probability of an event and I get the information content of the event, right? Right now I don't have that function. I'm just building some intuition towards that function, okay? But this is one requirement that I want the function to satisfy. This is something that all of us agree with, okay? Now think of two events which are independent, A and B, okay? So A is the event whether the AC is on here or not, and B is the event which tells you, oh, okay, maybe, sorry. So let's consider two different random variables. So X is the random variable which can take on values 0 and 1. So X is again this random variable which can take on these four values, A, B, C, D, whether who won in the tournament. And Y is this another random variable which can take on the value on and off depending on whether the AC is on in this room or not. Okay, what can you tell about these two random variables? They are independent random variables. Okay, so this is on or off, and this is which team won the tournament. Okay, now I come and tell you something about the random variable Y, and I come and tell you something about the random variable X. Okay, so now I want you to tell me this: what is the information content of X and Y? I tell you something about X and I tell you something about Y. And these two events are, these two random variables are independent. Then what can you tell me about the information content? What is the condition that you would want? You gained some information by knowing things about X, and you gained some information by knowing things about Y. Okay? So what can you tell me? It should be the sum, right? Because these two are independent events. So whatever information I'm getting from this random variable and this random variable, it's together enhancing my information, right? It's not cancelling out anything, or there's no common intersection there, right? If the two events were not independent, then I wouldn't expect this to hold, because knowing something about the first event already tells me something about the second event, right? Because they are dependent. So then in that case, the information gain would not be additive. Okay. So now let's see. I already made a case that this function which tells me the information gain is actually proportional to the probability. Okay, so that means this is what the input is going to be, right? And then what is the other condition that I want? Is this a fair thing? Right? I've just replaced information content by a function, and I know that the function should depend on the probability, because that is what we have established here. So we know that the function depends on the probability. We still don't know what this f is exactly, but I'm trying to impose some conditions on f. One condition of f is that this condition should hold. Okay, now let's look at this condition which I have underlined. This is f of Is this fine? Because the two events are independent, you can write them as the joint probability as p of x into p of y. Is this clear to everyone? Right? You seem to be a bit lost. Arvind? Clear? Okay. Now what is happening here? I have a function f of a into b, and that is actually equal to f of a plus f of b. What family of functions do you know which has this characteristic? Log, right? That's why log is a good choice for this. That's why information content is going to be the log of the probability, but I wanted it to be inversely proportional, right? So it will be log of 1 by the probability. Okay, so that's why information content of this thing is, so you see this, how did we arrive at this log formula? Okay, and this log can just be to any base, it doesn't matter. Okay, so all of you get how we arrived at the formula for information content? Okay, now just give me a minute, I need to think of what is the next thing that I have to say. Okay, fine, so we have found out the information content of one of these events happening, okay, which was the x taking on the value a. Okay, now let's think of this random variable x. So here actually I should have said x equal to a, probability of x equal to a. Okay, does it make sense? Because the random variable is x and the event is x taking on the value a. How much information content is in that? So if I know that x was a, how much will I be surprised by it? Okay, now let's take this event, this random variable x, which can take on values a, b, c and d. As I said, with each value there is a probability associated with it, such that this sums to 1. Okay. Now, okay, I didn't need to draw this diagram. Okay, I should have just done this. So x is a random variable which can take these 4 values, which each of these values I have a probability associated. Okay, so these are the values, these are the probability values. Now, what do I also have? I have the information content associated with each of these. Right? And the information content actually tells me the surprise of that event. Now, if I ask you, what is the entropy of this random variable x? So remember, I had this case where I was betting, and with every outcome I had a value associated with it. I had the same situation here. With every outcome I have a probability, and I also have a value associated with this, and the value is the information content. Okay. Now if I ask you, what's the entropy or the expected information content of this random variable, then how will you compute that? I'm asking you for an expectation, right? So I'll compute summation I belonging to A, B, C, D, P of x equal to I, information content. What's the formula for that? Minus, so I'll just take the minus outside. Okay, so this quantity is called the entropy of the random variable, right? It is the expected information content in the random variable. Okay, now if you see, what would be the entropy of a random variable if it's corresponding to a certain event? That means, say the sun rises always in the east, right? So what is going to be the entropy of that? 0. Why? You'll have one of the sums in the summation as 1 log 1, right? And every other sum would be 0 into log of something. So 0 into anything is going to be 0. Even though that quantity is not defined, 0 into anything is going to be 0. So the total entropy is going to be 0. Okay, so this is entropy. Now what is it that we are actually interested in? Cross entropy. So we have not gone there yet. Okay, so we need to perhaps add one more slide. So far everything is clear. Okay, so now we are interested in something known as cross entropy. So there again the situation is that there is something which is the true distribution and something which is the predicted distribution. Okay, now actually before going there, so let me just erase this off. How many of you have heard that entropy is related to the number of bits that you need to transmit something? Do you know why that connection exists? No, okay. Now again let's think of this, that you're trying to transmit a message, okay, and that message is again a random variable which can take on 4 values, A, B, C, D. Okay, so think of these as 4 commands that we are trying to send to someone, right? And then based on that command someone will take some action. Now in the digital case, how will you transmit this? Encode it to bits. So what is the encoding that you will use? 0, 0, yeah, we'll come to that. 0, 1, 1, 0, 1, 1. So how many bits are you actually using for every message? 2 bits. Okay, for every bit. So maybe this is A, this is B, this is C, and this is D. So for every message you are using 2 bits. Okay. Now, okay, let me just see. Okay, so let's see actually what, when you're doing this, what are you actually assuming? You're actually assuming that all of these are equally likely. If all of these are equally likely, can you tell me the information content of any of them? It's going to be minus log of 1 by 4. Okay, that's actually equal to minus log, and this is to the base 2. Okay, okay, 1 by 4 is just 2 raised to minus 2. That is equal to 2, right? So the information content is actually equal to the number of bits that you are going to use to transmit that message. Okay, now let's see if this is just in this spatial case or in a different case also. Suppose this could take 8 values. How many bits would you use? 3 bits, right? So you'll have 0, 0, 0, 0, 0, 1. Okay, and this would be A to H. Now what are you actually assuming here? Each of these is equally likely. What's the probability? 1 by 8. What's the information content? 2 raised to minus 3, that's equal to 3, right? So the number of bits that you actually use to transmit something is, you can talk of it in terms of the information content of that, right? Now suppose I want to transmit this over a long distance. Okay, so I need to be a bit efficient in terms of number of bits that I use, right? So now in one of these cases, suppose it's of the following form, right? That let's look at the case where x can take one of 4 values, and say, let me just put the right values. So I'll say 1 by 2, 1 by 4, 1 by 8, 1 by 8. Okay. Now what's the information content of each of these? 1, 2, 3, 3. And this is the message that I'm going to send. Okay. So what am I doing here? I'm using a different number of bits depending on the probability of that event. Why does this make sense? Why is this a smart thing to do? If you want to transmit something which you're going to transmit a lot of times, you better use less number of bits for that. And this is exactly what is happening here. A was having the highest probability and you're using the lowest number of bits for that. Okay. Now what is the expected number of bits that I'll use up? If it's A, I'll use 1. If it's B, I'll use 2. If it's C, 3, and D, 3. So what is the expected number of bits that I'll use? Again, I have the same situation, right? I want you to cast it into the same situation. I have the probability values, and with each of these guys, I have a cost or a value associated. What's the cost? 1 bit, 2 bit, 3 bit, 3 bit. So what's the expectation now? Can someone compute the expectation? 1.75. Right? Actually, let me just write it down. It would be, again, I belonging to A, B, C, D, P of x equal to I into the number of bits that you will use, right? So that is just equal to log to the base 2 of P of x equal to I minus 1. What is this quantity actually? This is the entropy. We just saw this, right? This is the entropy of the random variable. And what is it telling us actually? That the entropy is 1.75. So what is the meaning of this actually? So on average, you will be needing 1.75 bits. Whereas if you are assuming everything is equally likely, on average you are using 2 bits. Right? So you see that on average you are making some savings here. Right? So that's what the entropy tells you. If you know what the probability of these events is, then you better use that to decide the number of bits that you're going to use to send each of these. Okay? Okay, so now let's complicate this a bit more. Now we have the entropy. Now let's complicate it a bit more. So there is some true distribution which exists. There is some true distribution from which these messages are coming, right? But you don't know what that true distribution is. We never know the true distribution. That's the entire problem that we have been dealing with in machine learning, right? So what you will do is, we'll somehow try to predict this distribution. And the recipe that you will use is the same as that I used for the example where I had an urn, right? So there are these thousands of 10,000s of messages which are going to keep coming on. You don't have access to the entire stream, but you have seen some 1,000 of those messages. Just as I had peeped into the urn and I had seen some balls, and I had made an estimate that I think based on these messages that I've seen so far, I think these are the actual probabilities, right? So the true probabilities are say P1, P2, P3 and P4 corresponding to A, B, C and D. I don't know what these true probabilities are, but I can estimate them looking at some samples or basically using my domain knowledge, right? Maybe I would know that if one of these messages is stop, right, and I'm actually trying to talk to a computer or a computer program, then maybe stop is something which I use very rarely, only at the end of the program or something, right? So I have either some domain knowledge or based on some samples, I can estimate the value of this probability. And just try to relate it to the exact example of urns, where you had these 10,000s of balls, but you couldn't see all of them. You sampled some and estimated a probability. Here again, there's a continuous flow of message. You can't have access to all of these because they're going to continue. But you have seen some of those, and based on that, you estimate these probabilities. Now, based on this estimation, how many bits? Okay. So now this is the estimation that we have. Okay. Now, based on this, you will decide the number of bits that you'll use for each of these messages. Right? Because you have some estimate, so you want to be smart. You don't want to keep 2 bits for all of them. So you'll just say that I'll use log qi bits for the ith message. Is this a fair thing? Because I know that the information content is proportional to the probability. In fact, it's exactly given by this formula, minus log of qi. So based on my estimated probability, I'm going to do this. Okay, and this is the number of bits that I have reserved. Now, do you see a problem with this? This is my estimation. But the data is actually going to come from the true distribution. It's not going to follow the distribution Q. It's going to follow the distribution P. So now what has actually happened is this, right? This is the situation that we are dealing with. We have P, which was the true distribution. That is the rate at which the data will come. But with each of these events, the value that we have associated is now related to Q. Because Q is what I have access to. I don't have access to P. I just have access to Q. So I have associated a value based on Q. Does this make sense? I should have actually used log P1 bits, log P2 bits and log P3 bits, but I don't know what P1, P2, P3 are. I just estimated them based on some samples, so that is Q1, Q2, Q3, and these are the number of bits that I am using. Now if I have to compute the expectation, how will I do it? I'll have to use P because that's the true distribution from which the data is coming, right? So what would the expectation now look like? Everyone gets this? The actual probabilities are this, but because I am poor at estimating them, I ended up associating these values, which could be wrong, right? Because I would have overestimated the probability of one of these messages and hence I have reserved lesser bits for that, or underestimated the probability of one of these events and hence reserved more bits for that, right? Or vice versa, right? I could have assigned a wrong number of bits to them, right? P. No, so do we have access to P in the sense?
How do we know the values Pi when we compute?
Yeah, so someone knows that, right? I mean, there's again in the same case as in the label case, right? We have access to the true P there, and we are estimating a Q. When we are given these images for the training data, we know that the distribution is 0, 1, 0, 0 if the image is B for banana, right?
Experiment run and then it's validated.
Then it's validated, right? So now this is, what is this quantity called? This is called the cross entropy, okay? You get why it is called the cross entropy? Because now you have 2 different distributions involved here. Okay, you have the Q distribution based on which you made your decisions. You assigned values to these events based on the Q distribution, but the true distribution is the P distribution. So the actual number of bits that you'll use up on average is going to be based on the true probability, right? Try to understand that. Now what will happen is for event A, you have assigned a certain number of bits. Now how many bits will get used up? It depends on the actual probability of P. If that message is repeated many times, then that's how this summation would be computed, right? Is that clear? So this is called the cross entropy. But now why is this the difference between 2 distributions? That is what we wanted. Given 2 distributions, we wanted to be able to find the difference between them. Now I'm telling you that cross entropy is a way of finding that difference. Why is it so? So what would you want this difference to, what is the property that you would want this difference to have? If P is equal to Q, then if P is equal to Q, then not 0 maybe, it should take the lowest possible value. right? So this function, right, it is actually telling you loss of P comma Q, right, is what this is. And we're calling it as the cross entropy. This function should take its minimum value when P is equal to Q, right? Because now at that point you're not really making any loss. That's the best you could have done. Does this function take its minimum value when P is equal to Q? Yes. Why? How is that obvious? But why? There could be something else which is lower than the actual entropy, right? Why? How? You're trying to minimize something, so you have to give me an answer. Okay, so yeah, so let's do that. Okay. So to how many of you it's obvious that Q is the answer? I mean, the answer is P is equal to Q. It's not. Okay. Now this is the part which I'm a bit worried about, but I'll just do it anyways. So this is what we want to do, right? So, okay. So let me see, how do I put this? Okay. So remember that we had a P and we had a Q, and we want to find a Q such that this quantity is minimized. Okay, that is what our objective is, right? So we want to minimize this with respect to Qi. Okay. Now, how do I find the minimize? Suppose I have this problem. How do I find the minimum value? How do I find the value of x which minimizes this? Take the derivative and set it to 0. Okay. And then in this case, I'll get x equal to 0 is that value. Okay. Can I do the same thing here? And suppose it was this. So now this is a function of two variables. Again, I could do the same thing. I could take the partial derivatives and set them to 0, right? And I'll get the minimum value. Now here, this is actually a function of how many variables? K in general, right? So Q1, Q2, Q3 up to Qk. Okay. Now can you try doing the same thing? Can you take the derivative and set it to 0? This is again a sum, right? It's very similar to this situation, right? It's actually, let me just write it down. It's P1 log Q1 plus P2 log Q2 up to Pk log Qk, right? Now I want to take the derivative with respect to one of these guys, say Q2. What would it be? P2 by Q2 is equal to, what will I do? That's the derivative, P2 by Q2. I'll set it to 0. Do I get anything? What is it that I'm doing wrong here? There's something that I'm deliberately doing wrong. Is this an unconstrained optimization problem? There is a constraint on the variables. What's the constraint? So why my true optimization problem is minimize with respect to Qi's such that summation Qi is equal to 1. Do you know an easy way of dealing with these problems? How many of you know the Lagrangian multiplier? Okay, how will I use it here? What will my objective function become? Then summation of Qi minus 1 lambda, then minus. Okay. How many of you understand the intuition behind this? Okay, that's a good answer. Okay. Now let me try to explain why this makes sense, right? This is the constraint that we have. We have to operate within this constraint. Okay. What I've done is I've taken the, so now if the constraint is not satisfied, what will happen to this quantity? If the constraint is not satisfied, that means my summation is not equal to 1. That is what means by the constraint is not satisfied. What will happen to this quantity? It will be a non-zero quantity, right? Fine. then what will happen to my overall objective? I think we have made a mistake. This should be plus, right? Yeah, I should add it, right? Should be plus? No, it does, right? Oh, the lambda can be, oh, okay, sorry. Okay, so let me assume this is plus. Okay, so what I'm trying to do is that this is my objective function which I'm trying to minimize. I've added another quantity to it. If this quantity is not equal to 0, then I will not be the absolute minimum. I'll be at the minimum plus something, right? But if this quantity, if the constraint is satisfied, then this quantity will go to 0. Then I'm actually at the minimum of the function. Do you get this? Right? So this is the function that I want to minimize. I've added some quantity to it. Now that quantity is actually related to the constraint that I don't want to violate. If I violate the constraint, this is going to be non-negative, right? So whatever minimum value I achieved, I'll be slightly higher than that because some non-negative value has got added to it. Okay? Is that fine? But if the constraint is satisfied, then I can achieve the minimum value. So that's roughly the intuition behind using this Lagrangian multiplier. It's a very crude intuition, but there's of course a lot of math behind that, but I'm just giving you the intuition behind this. Which one? Yeah, that's what you could adjust the lambda and ensure that it's non-negative, right? Okay. So now can you do the same thing? Can you equate this to 0? Can you take the derivative and equate to 0? What will you get now? This term will give you pi by q2 as before. Oh, sorry, p2 by q2 as before, plus lambda times, yeah, plus lambda times 1. Okay, fine. So equal to 0. So then what will you end up getting? P2 is equal to, I think there's something wrong here. This should be minus P2 by Q2, right? So P2 is equal to lambda times Q2, okay? And then further actually, you can show that lambda is going to be equal to 1. How can you show that? No, constant is fine. So do you see how you will get lambda equal to 1, right? So what does it actually tell you then? P2 is equal to Q2. That means all, in fact, you can show that all Pi's are equal to Qi's. That means the distribution P is equal to distribution Q. So this cross entropy term will be minimized when your true distribution or when your predicted distribution is the same as the true distribution. And hence it captures the difference between the two. Okay? And that's exactly what we were interested in. We were interested in a quantity which can allow us to capture the difference between the true distribution and the predicted distribution. Fine? So we have arrived at that quantity, and that quantity is cross entropy. So therefore, for all our classification problems where we have this scenario that we are given the true distribution where all the mass is focused on one of the labels, and you are estimating a distribution where you could give non-zero quantities to many of those, and you want to find out how wrong your estimates were with respect to the true distribution, you can use cross entropy as a measure for that, right? So now your loss function which you wanted to depend on the difference between P and Q, it can just be the cross entropy between P and Q. Okay? Is that clear?